Hello everyone, Jason here with VC Edge. This video is going to be part 7 of the interface knife build, and I'm going to be working on some of the heat treated parts that go into the knife, namely the lockbar insert and the detent track and lock face that goes into the blade. So we're going to machine those out. It'll be made out of some 440 stainless steel, and then we'll heat treat them to try to get the hardness that we want, and then they'll be ready to put into the knife. Before I do that, I have to do a slight modification to the machine. If you've noticed in some of the videos, the coolant will do this. From the time the coolant pump comes on, it takes a few seconds for it to get to the nozzles. So that's a problem. It'll actually start machining things before the coolant turns on. And with certain materials, it's bad for the surface finish and bad for the tools. So I'm going to install a little check valve. It just needs to go somewhere in the system. And so I think I found a good spot to put it. Let's go take care of that. Right here at the outlet of the coolant filter is just a fitting that I can replace with the check valve fitting. And it doesn't really matter that it's not at the nozzles, as long as it's somewhere past the coolant filter, which kind of acts as a reservoir. And what's happening is that when all this drains back from the nozzle, it has to refill all these lines. And it has to go all the way from the tank, all the way up to the top and then down into the nozzles. If it does drain at all, it'll probably just be from the very top of the system up there and down to the nozzles, and it'll have to refill that portion, but that's not very far. I'm going to do a little test first, see exactly how long it takes right now, and then put this in and see what the difference is. Okay, about 2.5 seconds from a semi-primed line. Let me let it drain for a while and try it from like a cold start if it's been sitting for a bit. Okay, so that's the worst case scenario if it's drained back all the way after sitting for a little while, about 5 seconds. That's a good amount of time. Gotta take this out. Got a bucket down here. Hopefully catch. There you go, a little bit of coolant there. Pull this guy out. This one has a seal on it, like a rubber seal. This one doesn't, and it's made out of plastic. It's made out of Delrin, so it's the good kind of plastic. It actually will withstand the types of coolant that's in the machine. This coolant filter body actually is made out of polystyrene, which is a bad material to put into a coolant system. It'll last for a while. I didn't realize at the time that I ordered it that it was made out of that, but I've got it. I might as well use whatever life it has, although I will need to replace it before it breaks apart. I'll have to get a one that has a nylon body or a metal body one, either one. So I'll have to replace this sooner rather than later, but the check valve will hold up. It'll be fine. Also, because it's made out of plastic, I will be using, instead of trying to torque it down to seal it like you would normally with a pipe thread, I'm putting a little bit of silicone on it so I can just gently tighten it, and that will seal it up. Of course, this isn't big enough. I'm gonna go get another one. Good to not put it on the inside of the threads, because then it'll force it inside, and some of the sealant could get into the check valve. I don't really want that. So just on the outside of the threads. So any squeeze out will go to the outside. Just gonna tighten this up a reasonable amount. That's probably good. And then reconnect this guy. Yeah, it looks all right. Okay, so I'm actually going to let this dry completely, and then we'll redo the test. Hopefully it works. All right, here we go with the check valve installed. I did run this real quick just to make sure that it wasn't leaking or anything. So I'll see how long it takes to get the coolant to the nozzles. Okay, so it's a little over 1.5 seconds. It's quite an improvement over the 2.5 seconds that it took before. So I'll take it. Let's try machining some stuff. So we got our 440C stainless steel, just a piece in here that's it's big enough to do 6 parts, just as a sort of a test. I was able to nest in the model, the lockbar insert and the detent track lock face, 6 of each into this one little part. So it's going to machine out quite a bit. We're using 10 different tools to do all this. Got a couple different drill bits, ball end mill, 82-degree chamfer, thread mill, 16th inch end mill, 8th inch end mill, the 20 thou end mill, 3 flute modular, a little engraving tool that I used to do some of the other features that I'll show you. And yeah, takes quite a bit of tools. It almost fills up the whole tool tray. All right. Alright, these parts are done. You can see I've got both of the pieces nested in there. And there's a little bit of a burr on some of these, but that's not really too big of a problem. You can see I faced the whole entire top of this, so now I have the thickness to the exact dimension. Flip it over, and then zero on the same spot that I zeroed before. There it is, flipped over. All I have to do is re-zero the X. First time I zeroed it over here. So since I flipped it, just got to re-zero here in the same spot, no big deal. Pretty easy. The Z and the Y stay the same from where I had it. Also, the coolant is definitely reaching the tool before it starts cutting, like in plenty of time. So that's working really well so far. Alright, so here are these parts all machined out. I guess I should probably explain what they are. So we have the lock face and detent track, and then the lock bar insert here. So here's one in a blade. The detent will ride along this face on this hardened surface. As the knife is, when it's closed, the detent locks into this little hole, and then when it's opened, it slips out of that, rides along this surface, and then the lock bar insert will touch against this surface and lock it open. keeping them in this frame for heat treatment. It's just a lot easier to handle, and they can be at the same heat treat hardness. There's really not a good way for me to check any of these features to see if they're the right size. I can check the threads right now and make sure those work, but these features are so small that it's really almost impossible for me to check to see how they're going to work out until we put the knife together. You can see how it's going to go in there. It just bonds into this little slot that I machine into the carbon body of the blade. As the name implies, the lock bar insert sets into the lock bar, into that little spot there. And so you can see the little detent right there. I'll explain more about that later. This really affects how the knife will function. This is the whole mechanical mechanism of opening the knife. I'm aiming for a hardness of somewhere between 57 and 60 Rockwell. I've gotten that in the past and it's been working out really well in the knives I've made so far. You can just slip this into one of these little stainless steel bags. It's sealed up around 3 ends. You just got to seal this one up. That keeps the oxygen from getting inside, and it just keeps it from getting a bunch of what's called forge scale built up on the outside of the parts. So they should come out nice and clean. May have a little discoloration, but that's all right. This is the heat treat oven. This one's from Even Heat, and it's just about the right size for the parts that I'm doing, which is to say it's pretty small. Just got to set the controller up for the right temperature. According to my notes, which, you know, it's always a good idea to take notes when you're doing all these heat treatments, because your parts can vary from what the manufacturer of the steel will recommend. Be 1400 degrees for 20 minutes, 1900 degrees for 30 minutes. This is a plate quench, and then after that I can do 2 cycles of tempering at 400 degrees at 2 hours apiece. So it's kind of a long process. I'm not going to show much of it except maybe taking it out of the oven after it's all red hot. And it goes in cold. And then the oven is programmed to ramp up at a certain rate and do the cycles that I tell it to do. One thing about this controller, I kind of wish I'd have gotten the fancier one. This one's kind of a pain. It's sort of like the Office Space printer.
PC load letter? What the fuck does that mean?
It's got all these symbols and things that it tries to tell you what it's doing, but it's kind of hard to understand unless you really know what you're doing. All right, here we go. Just a couple minutes left. You gotta kind of be Johnny on the spot with this thing, because as soon as it's done with the program, it will just start cooling down immediately. As soon as it's done, I'll pull it out with these long pliers. There's a reason I've got long sleeves on and leather gloves. This stuff is hot. Just being next to the open door is uncomfortable. But I'm going to do a plate quench, which is basically just taking a couple of aluminum plates that are room temperature, which in this case is a climate controlled 68 degrees. So should be done any second. I'll just take it out, put it on this aluminum block here, sandwich into this other aluminum piece, and that's the quench. It's okay, it's done. Here we go. There she is. Set it on there. Eventually I'll get one of those arbor presses to do this. Hot, hot, hot. I think you're supposed to let this cool down to about 100 degrees or so, and then put it into the tempering oven. But I don't have a separate tempering oven, so I gotta let this thing cool down, and then I can put it into the tempering cycle, which is only at 400 degrees when this is starting at 1900, so it'll take a while to cool down. And then we can do the tempering cycle, and then we can check the hardness on it and see what we ended up with. Last time I did this, I think I got it to 58 Rockwell. We'll see if it worked the same way. So So I'm gonna leave this door open partially. Look at that, still just red hot. And it stays that way, all that ceramic in there. We got the parts out of the heat treatment. A little bit of discoloration on a few little spots, but nothing too bad. It looks pretty good overall. And I'm gonna check the hardness with the Ames hardness tester. This thing works pretty well. It's a little bit subjective, but it'll get you within 1 to 2 Rockwell, depending on how good you are at it. And it works the same way as most other hardness testers. It has a little, for Rockwell C, it has a little diamond tip here, puts a little dimple into the material, and measures how deep that dimple goes, and the deeper it goes, the softer it is. So I'll just try this on one of the sections of the material that's a little bit thicker. You got to make sure your eyes are lined up exactly the right way. And this isn't exactly a tutorial on how to use this thing, so I'm gonna do it and then tell you what the hardness ended up being. .56 Rockwell. .57. So tested a few different spots, getting 56 to 57 Rockwell, which is good for these parts. You don't want them to be too hard. Also, they need to be hard enough so they don't wear down real easy. Now that I know I've got the hardness within the range that I specified, need to pull these out. But normally you would cut tabs off. One of the nice things about these hardened parts is that you can just sort of, if the tabs are fine enough, you can just snap them. And the parts will come out. Just gotta sand those edges off. Pretty easy. This one will probably just break. Yeah. A little bit of sanding and deburring. These parts are ready to go. The way the detent works on these is a little bit different from other knives. I have what would normally be considered the detent ball milled into the lockbar insert, and it's not actually a ball shape at all. Let me see if I can find some way to demonstrate this. Alright, this should be big enough. If you think of this as the detent ball, this would normally be pressed into the lockbar insert or into the lockbar somewhere, about like that. So that much would be sticking out, or somewhere around there, depends on how deep you bury it. And then you have the detent hole. This would be like the side wall of the detent hole. And what happens is it falls into the detent hole, and then that locks the knife into the closed position. Then when you want to deploy it, it has to slide up over this detent, and then the knife opens up. The problem with this type of mechanism is that the exact position of this will change how much pressure it takes to open it up, and it has to kind of roll off. A lot of people will slice the top off of this so that it only has to roll off like a little bit, and that works pretty well. This whole thing works pretty well if you get it set exactly right. What I don't like about these is that you end up having to put, this is the lock bar pushing in, you end up having to put a lot of lock bar pressure against the hole to hold it in place. And then so when you open it up and this is dragging on the detent track, it's pushing a lot of pressure on it, creating a lot more drag. So I'm going to try to reduce the amount of pressure that it takes. So the way that my detent mechanism works, if we have the detent hole, the side wall of it, and then we have another ramp that comes up to it, and when you put pressure against it, if they're both at an angle, they will slide apart. This is very similar to the way like a firearm trigger works. It has a couple of ramps that hold against each other, and then when you release the trigger, they slide apart. Makes for a nice, crisp, clean breaking point. So what I have is a cone shape, and then a similarly angled slot. So if I set these to the right dimension, I put pressure against them when I open the knife, and then they will slide apart, and it deploys really fast, and it doesn't take a whole lot of pressure to maintain this these two being in the closed position. So that's kind of how it works. Hopefully that explains it a little bit. These turned out pretty good. This little notch here is just for a locating feature so that it can be located into the blade body in the correct position. That has to be very tightly controlled because of that detent mechanism having to sit in a certain spot. So that's it for those for now. We'll see more of those later. I've got this face polished down to about a 800 grit. Should be nice and smooth for the detent to ride against. Seems okay. We'll see how well they fit when we get the blade body ready to go. So that's it for this video. Those parts are all done. They're looking pretty good. We'll find out how well they fit later on when we put the rest of the blade pieces together. And speaking of which, the next video we're going to do the blade cutting edge itself. And so we're going to machine that, heat treat it, and then do some hard milling on it. So that should be interesting. And with that, I'll see you on the next video.